Yeah, what's up, everyone? Good evening. How you doing? I hope you had a beautiful Sunday. You're welcome to this class, our very first class on normal distribution. So we have a couple of things to talk about, and seeing that this is the very first class, you need to understand that you have to be very attentive and focused, and don't shoot yourself in the leg. Make sure you get calm. You're not going to have the whole knowledge once. It's possible you may not get it the very first time uh we mention it, but you can just stay put, and in some few minutes everything will get very clear. So please stay very focused. I really want to delve into this very interesting topic. This is a very interesting yet consequential topic in major exams, and I really want to clarify every bit of intricacies around it. It's very simple, yet if you don't have the real basics, you will have issues. It's just that simple. Guys, please make sure you stay as attentive as you can, because this is the very first class on normal distribution. All right. First of all, let's start from a different name you may see this being called. Another name this could be called is the Gaussian distribution. All right. Gaussian distribution. And as I said earlier in some of our classes before now, I told you guys that when we talk of discrete distribution functions, we talk about Bernoulli binomial, we talk about Poisson, we talk about geometric and some others. Of course, the four is what we limited the classes we have done to. But I said, when we talk about the continuous distribution functions, one of the most extremely important continuous probability distribution is the one we're considering in tonight's class, and that's the normal distribution. It's a very extremely important one because it mirrors and it models the our day-to-day living. So it's one of the most important, extremely important distribution we study in statistics. Now, how do you relate with a normal distribution? Number one major description of a normal distribution is it is symmetric. A normal distribution is symmetric. And not just symmetric, but it's symmetric about the mean. And I will explain to you what that means. A normal distribution is symmetric about the mean. All right? Let me explain to you. Number one, let me try to remind you of the word symmetric. If you have forgotten, I told you guys some times back that I gave you distribution shapes, and one of the shapes I drew for you, if you can recollect, is a symmetric shape. Can anybody in the comment section give me another name I called the symmetric shape? Anybody? There's another name we can call a distribution that has this shape if we don't want to use the word symmetric. Anybody? Can anybody give me another name for, instead of saying symmetric, is there something else I can say? Nobody? All right. Symmetric or bell-shaped? I told you guys bell-shaped. You check your notes, you will see this there. All right. So you can say symmetric, you can say bell-shaped. Now, what's the real understanding of the word symmetric? Symmetricity of a distribution comes with one important value. We said symmetric about the mean, meaning that this point right here, which you can see divides the shape into two equal parts. You can see that this point right here is the mean. All right, this is the mean. So that's why we say it's symmetric about the mean, because the midpoint, which I'm sure as you heard me say the word midpoint, I'm sure you agree with me that if this is the midpoint, if I was running this in a different, if I'm talking about this in a different way, I can also call this what? The median. I'm sure you recognize that, because if this is the midpoint of a distribution, this obviously will be the median, but it's the mean also. And that's why we say it's symmetric about the mean. These are just some properties of normal distribution that you have to take note of. Number one, the mean is equals to the median. But not just that. Can you guys think about something else that is also, this point is also represented by this point right here, of course, which I highlighted, this point that divides the shape into two equal parts. What do you feel this place can also be that I have not mentioned? Is there anybody there? What do you feel this place can also be? Anybody? Of course, this is also the mode. So you can see that one of the important property of a symmetric distribution is that the mean is equals to the mode is equals to the median. You can see that's very important feature, that we have the mean, the mode, and the median as the same. This is a very perfect objective question. You would see where they will tell you to distinguish between different expression and which one, they will ask you which one represents a symmetric distribution. Of course, the option that told you that the mean is equals to the median equals to the mode is the perfect one, because that is an important feature of a distribution being symmetric. All right, that's that about that. So this is when you hear the word being symmetric about the mean, that's telling you that the midpoint, the mean, is going to be a dividing line between the two different equal parts of the distribution. And also it will also represent the median as well as the mode. All right, so this is just, of course, we're introducing, so be very attentive, as I said. Now, the next thing we need to talk about, because if you recollect, first of all, don't forget that I told you guys that this is very essential in our day-to-day living. You will see several questions we'll be solving and how much they represent real-life experiences. Now, with everything we have been doing, when we talked about binomial, Bernoulli, Poisson, and geometric, there's one thing that we did throughout. If you guys can recollect, we always stated their PMF. All right, we stated their PMF, meaning that if we're talking about normal distribution, we have to state the PDF. Don't forget, I told you guys that discrete probability distribution function, we tend to use the word PMF, probability mass function. Whereas when we're talking about continuous distribution function, like the normal distribution, we say PDF. That's probability density function. So we say probability density function when dealing with continuous. So the PDF of a normal distribution is quite very unique. And I want you guys to be, you don't need to get scared. Of course, it's what it is. So we have it as 1 over sigma square root of 2 pi e raised to power minus 1 over 2 sigma square. Let me erase this. Of course, I believe you have taken note, 1 over 2 sigma square, then x minus mu all square. So right here is the PDF of a normal distribution. So you can see it right here, very simple and beautiful to see. 1 over sigma square root of 2 pi e raised to power minus 1 over 2 sigma square x minus mu everything all square. All right. Now I need to introduce to you, of course, there's something I'm missing out here, which you guys should always be attentive to. Whenever you state a PMF or a PDF, you must always give the band for your x. Your x cannot just take any value. So for this PDF, of course, your x, this is the value for your x. And don't forget, the value for your x, the values for your x ranges between minus infinity. We can say for x being between minus infinity to infinity. Now, let me give you a quick check back on some of the things we learned earlier. I told you guys that one of the precise difference between discrete and continuous is that discrete has to do with countable data set, whereas continuous has to do with measured data set. So when we're talking about discrete, we talk about whole numbers, 0, 1, 2, 3, 4, 5, and so on, to be minus 1, minus 2, minus 3, but we never talk about decimal. But you see, when you're dealing with normal distribution, you have to always highlight it in bands. All right. So you see what we have right here, as I always told you guys, this is just representative of a model. You don't have to, minus infinity and infinity here just represents that x can take any value on the positive side and it can take any value on the negative side. So it's not restricted by anything. This is different for some other for some other distribution we have talked about in the past. For instance, if you recollect, when we're dealing with geometric, our x value starts from 1. All right, 1, 2, and so on. We cannot have 0 in geometric distribution. Of course, if you go back to the video on that class, you'll be able to understand what I'm saying because of the peculiarity of the distribution and its properties. Now, if you look at that of binomial, we said x ranges from 0 up until n. The bandwidth for x will be from 0 till n. It terminates at n, the number of trials. That of Bernoulli, x is always 0 or 1, one of the two. It cannot be more than 1 because we only have one trial in Bernoulli. For Poisson, we have x being between 0, 1, 2, and so on. Because we don't have number of trials in Poisson, we don't talk about an endpoint being n or whatsoever. It all depends on whatever the nature of the question is. All right. Now, for your normal distribution, we have our x being between whatever value you have on the left-hand side and whatever value you have on your right-hand side. That's the meaning of the minus infinity to infinity. Now, another thing we need to talk about is, first of all, what is the representation of this sigma we have here? I'm sure you guys should be very much aware of what sigma represents. Sigma represents the standard deviation, all right? And sigma square is what? The variance. All right, so standard deviation sigma square is obviously standard deviation, and then sigma square is variance. Your sigma here takes value that must be greater than 0. That's the uniqueness of this distribution. The sigma is greater than 0. All right. Now, for your sigma square, of course, if the sigma is greater than 0, you know that if you square whatever value is greater than 0, the sigma square will also equally be greater than 0. So these are some of the things you need to note to understand, to make sure you are in line and to have proper understanding of distribution. And as always, you know, I don't always like to leave any stone unturned, especially at the beginning of any explanation, to ensure that you are very sound in whatever you are doing. Now, I want you to understand, you can see right here that we have a mu value, I want to explain everything we have here. Mu, that's the mean. All right. It has its uniqueness is that it takes values between infinity to minus infinity too. Let me put this in a box so that you don't mix it up. Let me put this. Let me put it in a box so you don't mix them up. So your mu is between minus infinity to infinity. The meaning of that essentially is just saying it all depends on the nature of your question. Your mean could be take any value on the left hand side and on the right hand side. All right. Don't get scared. You will not be using so much of this formula at this your level. But of course, any other person watching this video not doing the A-level JPEG should understand that this is a formula you would use often. But there is a limitation, a restriction to the coverage under the JPEG syllabus. So obviously, this is just for knowing sake. You will not be using more of this at this your level. But of course, you need to note it because you're going to be doing more of distributions in the future. You'll be needing to understand the application. Now, of course, the pi that is here is the normal pi. Of course, you know what pi is. I've talked about sigma. E is obviously exponential, what you're going to press on the calculator. Sigma square is what we have talked about already. That's this variance. Mu being the mean. X is what I defined already earlier. Yeah, so good. This is great. So we are done with this quick introduction to this aspect. Now let's talk about something else, some other properties of the normal distribution. It's very important you understand some key features. So I will be rubbing off this PDF. I want to focus on something else. So let's talk about something else. I'm sure you guys you paid attention to what we just said. The key to understanding any topic is being very patient and ensuring that you follow through on everything we're saying. Now let's talk about some feature of this curve we have right here. Now, just pay attention to something I'm going to do right here. Not this. Let's add. Okay. And let's have another one here. Okay. Then let's have one here. Okay. Now, these are different divisions I made. They are very essential for something. Now, look at something. We already defined this midpoint as mu. That's the mean. Believe you all followed at that point. This is mu. Now, I already talked to you guys about standard deviation. I want you to understand that you see this point here, from year to year, from this point you're seeing right here, that's the mu, till this first red line will be one standard deviation. So from year to year is one standard deviation. All right. That means, of course, if from year to year is one standard deviation, that means this point right here, if you can follow through, will be mu plus this point right here will be mu plus one standard deviation. You can understand what I just did. If this point is mu, I told you guys that from year to year is one standard deviation. That means it's more like saying if I said this point is 5 and I said this point from year to year is 1, of course that means this place will be 5 plus 1. That's just what's happening here. So if this place is mu and from year to year is one standard deviation, that means this place will be mu plus one standard deviation. All right. And if you look at that, this place to this place also will be, of course, one standard deviation. That means this place now, if you guys can guess, will be mu minus 1 standard deviation. I'm sure you agree with that. It's more like if I said this place to this place is 5 is 1, that means this place now will be 5 minus 1. That will be 4. It's just simple logic. If this place is 5 and we say from here to here is 1, of course, from here to here will be 1 also. That means this place will be 4, this place will be 6. That's what we just identified here. Good. Now that you understand that, of course, what we say right here is that mu minus 1, that's this point right here, which you can all see. Mu minus 1, that identifies with 1 standard deviation below the mean. This is the mean. So if this is mu minus 1, that's 1 standard deviation below the mean. Whereas mu plus sigma, mu minus sigma is 1 standard deviation below the mean. Mu plus sigma is 1 standard deviation above the mean. I told you guys already that from here to here is 1 standard deviation. That means this is 1 standard deviation above, bigger than the mean. Simple. And from here to here will be 1 standard deviation lesser than the mean. That's why we say 1 standard deviation below the mean. Very simple. Good. Now let's try and use dots to shade these points everywhere we just talked about. You can see we just identified, 1 standard deviation above and 1 standard deviation below. Now this thing I want to talk about next is very essential because you'll be needing this understanding very soon. Not probably for this particular thing we were saying, but to understand the whole concept around normal distribution. Now, you need to know that, don't forget, guys, that of course we have done this before. I told you guys that, let me see if you guys can recollect this. What's going to be the total area under this curve, guys? Can anybody shoot the answer to me quickly? What's the total area under this curve? Anybody? What's the total area under the curve? I'm waiting for answers. What's the total area under the curve? Somebody said 2. What's the total area under the curve? Zero? Really? We talked about this when we're dealing with continuous distribution. 0, people are saying 0. 1, what's going on? The total area under a curve is 1. I told you guys that already, and that's the reason why we said when people are writing 0, total area under the curve. Really? Really? I told you guys that when dealing with continuous distribution, of course, a function brought about the curve. This curve did not just happen. A function made it happen. If you have f of x being something, we then said for you to get different probabilities, we go on to, if you want to get the probability from maybe year to year, we say you integrate the function with respect to that band, whatever the band was. Then I told you guys that if you want to get, of course, if the total band was, let's say, minus infinity to infinity, let's just put that as a model. If you integrate the function with respect to the total band, that means the beginning, the last point here, and the last point here. If you integrate that function, you must get the value of 1. I told you guys that already. That's quite very basic. The area under the curve is always 1. And that's the reason why we said if something is a continuous random variable, the integral of the function with respect to the band, the limit you have, must be 1. It's a basic knowledge, all right? Now, what I said that to say this, if the whole area under the curve, all everywhere, if we could shade everywhere, if the whole area under the curve is equals to 1. So I want to talk to you about this particular area, what it will always be. So now that means if you ask a question, any objective question, and you're told to talk about the area that lies between 1 standard deviation above and below the mean, that's this point I just shaded. all this point I just shaded now, this area is going to be 0.68. Note that standard, this is by standard. That means, the whole area, this whole area is shaded in black, below and above, one standard deviation below and above, this area now. So if this whole place is 1, this particular place I shaded is 0.68. Note that. Very, very important. It's a very important thing to note. That means that area, the area in between mu minus sigma and mu plus sigma is approximately equals to 85%, sorry, 68% of the area. All right. So this mu minus sigma and mu plus sigma, the area it takes is always 68% of the whole curve. All right. Note that. Now let's talk about the next one. Of course, if this is always 1, 1, so that means this place now, particular one will be mu minus 2 sigma. So if you understood that from here to here was 1 standard deviation, that means from here to here will be 2 standard deviation. From here to here, 1 standard deviation. From here to here, another standard deviation. So that means if this place is mu, this place will be mu minus 2 standard deviation. More like, just understand it like this. Let me use this other one. If I have 5 minus 1, and all these places are 1, 1, of course, you expect that this place should be what? 5 minus 2. If this was 5, this is 4, this will be 3. So that's what is just happening here. If this is 5, this is 1 standard. Let's say this was mu, this is 1 standard deviation, this 2 standard deviation. So this place will be 5 minus 2 standard deviation. That's how we got this. And this other place will be mu plus 2 standard deviation. All right. That means this particular spot is 2 standard deviation above the mean. And this particular spot is 2 standard deviation below the mean. This is the mean. This is below it. This is 2 standard deviation above it. All right. So let's talk quickly. Let's try to shade that whole point. Let me use this marker now. So everywhere now, including that black spot, everywhere I'm shading now, in blue, everywhere I'm shading. Of course, the place that encloses, the place that mu minus 2 standard deviation and mu plus 2 standard deviation encloses, what's going to be that area now? So I've talked about this other area. So let's try and talk about this area. So this area that is enclosed by mu minus 2 standard deviation and mu plus 2 standard deviation is 95% of the whole area, 0.95. So imagine, let's try and ignore this. I've spoken about that already. So let's say we are dealing with this whole area now. All right, this will be 95% of the whole. So if this whole place is 1, this place will be 0.9. This place that we have shaded is 0.95 of the whole curve. All right, 0.95 of the whole curve. Now, 0.95 of the whole curve. Note that, so that if you are asked in an objective question, an MCQ, now what's the area between 2 standard deviation below and above the mean? That area is 0.95, 95% of the curve. Now, that's that about that. Let's see for the last one. Of course, can anybody tell me what this place would be based on what I've been explaining? What do you think this place would be? This will be mu plus what? Tell me what this would be. Mu plus what? And this place will be mu minus what? Can anybody give me an answer there? Yeah, this will be mu plus 3 standard deviation. Mu minus 3 standard deviation. All right, that's just the whole basic. Now let me talk about the area. Of course, let me take this out now, and let's assume we are going to be shading every of this now. I'm talking of everywhere, but don't forget we have not shaded everything. There is still a small thing left. So this area, obviously, as you can guess, will be almost 1, but not exactly 1. That will be 0.997. So So this whole area shaded, everything from here to here, everything is 0.997. That's obviously 99.7% of the area. So that means 99.7% of the area lies within 3 standard deviation of the mean. That's just the conclusion. 99.7% of the area lies within 3 standard deviation of the mean. So this is a very important property that I want you guys to note. All I'm trying to explain here is an important property that comes with normal distribution. Of course, I told you already that one of the basics of normal distribution is that it's symmetric about the mean, meaning that this midpoint, which is always going to be the median and the mode, is the mean. But we are going to focus our attention more on it being the mean. So, and I told you guys that from here to here is 1 standard deviation. Of course, if you can look at this same measurement, this same place, this will be 1 standard deviation. Of course, if this is mean, this particular spot will be mu plus 1 standard deviation, while this particular spot will be mean minus 1 standard deviation. Just basic. I try to explain it using a number line here. If this was 5, of course, if this point represented 1, that means this place will be 5 plus 1, and this place will be 5 minus 1. Of course, that's no brainer. If this was 5, you expect this place to be 4, you expect this place to be 6. If the dimension was counting in ones. All right. Now, if you're talking about the other side, that means 2 standard deviation above the mean, 2 standard deviation below the mean, 3 standard deviation above the mean, 3 standard deviation above and below the mean. So that's just basic. I just want you to, as I told you guys already, this is all introductory, and all these properties are things you don't say, how do we get? Like, for instance, you trying to say, how do we get this? This is just normal understanding. You don't need to crack your mind around this. It's something I'm telling you that is happening. That if you have 3 standard deviation above and below the mean, the whole area that will be covered by that band, all this place now that is shaded, is 99.7% of the whole area. It's not something you need to work on. How did you get it? It's something you need to just know that that's just it. I told you guys that the one standard deviation above and below is 68%, that will be 0.68. That's standard. You're not trying to get that. It's something that I'm trying to tell you works. All right. It's not something that you are going to learn how to get it. You can get it if you can go with trying to prove it. It's provable, especially if you have a computer to do that. If this whole area is 1, the 1 standard deviation above and below will occupy 68% of the whole area. It's just basic, but you don't need to wrap your head around that. All right. But the one for 2 standard deviation above and below, I told you it occupies a space of 95%. That's 0.95. And the other one, 0.997 is 3 sigma below and above the mean. So it's all basic. It's all basic. These are things you just need to understand. This is the first class, so you don't expect that everything comes very. Of course, you don't know anything about this. So these are things you just note on your left hand. I'm trying to just make sure we talk about this so that at least there is no confusion in the future. So this is all. Just start getting familiar with this curve. It's a very interesting one. Very interesting one. All right. Now, let's get on to something very important. We have all right. So we have we always talk about we said a random variable x follows a Bernoulli, and I told you guys that the parameter there is parameter P. All right. And we said a Bernoulli, a random variable X follows a binomial. And I told you guys that this will be N comma P. These things are very important I'm writing because sometimes you're not always going to be seeing it as, sometimes they will just say X follows a binomial and they wrote 10 comma 0.01, something like that. So you need to know what all these things mean. All right. And we have the next one follows a Poisson, and we have the parameter there as lambda. So whenever you see something and we have Poisson, and probably they just wrote 3. So you need to understand that the word 3 there, the 3 there is representing the parameter lambda. All right. And we have that for geometry. The parameter in for geometry is P, probability of success. All right. So let me touch that for normal. Of course, note all these things, very, very important. You don't always get familiar with the use of the word probability of success or this. They may just write it in this form and expect you to bring out the values yourself. So for that of a normal distribution, it follows a normal distribution. This is how you write that of a normal distribution. The parameter is mu and sigma square. This is the way you write that of a normal distribution. All right. So when you have a question on normal, just note that the way its parameter is written is in this way. So that means if you see something like this, X follows a normal distribution, and you see, for instance, let's say they wrote 5 comma 1.5. Of course, you need to understand that the 5 there will be representing the mu, that's the mean, and 1.5 representing the variance. Now, I need you to understand that sometimes we have different forms. Some people tend to sometimes want to write the form as this, mu and sigma. So it's all going to be indicated in whatever you're dealing with. If you're using a table, and the table may tell you that this is the format we are following. So I tend to follow this format, but whichever one, this is still okay, this is okay. But just note that you could see any of these two, don't get confused, all right? Now, there's something very important I need to talk about next. This is now the meat of the whole thing. Everything we have been saying is just basic property, and you need to really, really understand the next thing I want to talk about. This is now where you tend to see questions, and this is where you will be really tested in your understanding of what I want to say next. All right. Now, when we were dealing with continuous random variable, I told you guys that when you have a curve, if you're told to find, for instance, the probability of, let's say this is 5, 10, 15, 20, 25, for instance. If you are told to find the probability that the random variable is between 10 and between 25, you are told to find this. I told you guys in that class that what essentially they're asking you to find is the area under the curve. That's what I told you guys when we were dealing. If you could find the area under this curve, of course, between the 10 and 20, if it was 15, that means you'll be finding the area from 15 to 25. So the whole understanding is when you see a question like this under continuous random variable or continuous distribution function, understand that you're trying to find the area between that band. So in this case now, if it was 10 to 25, you're trying to find the area between 10 to 25. Now, I told you guys also in that same class that you don't tend to have the opportunity or the ability to find the area under this curve generally. So most of the time, what we do is to go on to integrate the function. So we integrate whatever function brought about this curve, setting the limit between the band we are trying to find. That was how we used to evaluate these questions. All right. We used integration, integrating using the band we were given to find a solution. That's the way we used to solve questions like this. I'm sure if you have been following, you can really understand what I'm saying. Now, but there's another way we can solve this question, and that's the use of a table. All right. The use of a table. I sent you a piece of the table some moments before this class. I'm sure you just I'm sure you of course you will not be using it so much this night, but if you see the table, you would see it has different numbers in it. So those numbers represent different probabilities, the answer to different probabilities, which I'll be explaining to you, not in this class, but some other classes. All right. So another way of finding, all I want to say here is another way of finding this question, of solving this question without having to integrate, which is what you have been doing in the past, is by using a normal table. And that's what we want to be delving into in subsequent classes. But what I want to do majorly in this class is to teach you a very important thing you must know how to do if you are going to be able to solve questions like this. All right. Now, this is a very big problem that used to arise when talking about normal distribution. Just pay attention now, you would understand what I'm saying. Now, I told you guys already now that a normal distribution follows we have the mu, and let's use standard deviation as that second parameter. Now, take a look at something now. I just said now that if you have followed what I've been saying so far, you would see that I said for us to find this probability, we can decide not to move through the route of making integration of the function with respect to the limits based on the bands that was given in your probability. Now, you have this. You can do it by using integration if you have the opportunity to. But another way of solving this is by using tables. All right? Using tables to solve it. Now, but there's a problem that can arise from what I just said. And the question is, how do we find area under a normal curve? Now, look at something. This is a possibility. Guys, pay attention to what I want to say next. I will try and draw as many diagrams as I need to get this very clear. Let me make this space available. Now, look at this particular, what we have right here. Let's say we have another one with 10 and let's say 3.5. Let me write a third one that we have a normal distribution with, let's say 12 and 3.8, just an example, all right? Now, this is the problem that arises from us trying to use a normal table. If you check your normal table, of course, that table I sent to you is what we call a standard normal table, because that's a way standard normal table. I will explain to you the reason why we have that. The reason why we have a standard normal table is because of this problem that comes with a normal distribution. Don't forget I said standard normal table. I did not say normal table. Let's assume we don't have a normal distribution. What would have needed to have done would have been that for every of this kind of question, now the mean is 5, the standard deviation is 1.5. We would need a separate table, just like what I sent to you now. We need a table for when the mean was 5 and the standard deviation was 1.5. There will be a table for that. Then that table is now what you will use to find answers to whatever question arise from a situation like this. But look at the problem that will come as a result of that. What about when you're not dealing with that parameter again? Now you're dealing with a new parameter of 10 and 3.5. If you see the table I sent to you, you will see they drew a curve, a normal curve there. But imagine you have a different parameter. That means you'll be needing a different table for when mean was 10 and standard deviation is 3.5. And let's say now we have to go on to, they say, okay, that question, we're done with that question. Let's say you just had a question to solve it. Then they give me another question and they say, okay, in this case now, the mean is 12, the standard deviation is 3.8. That means you will need a different table that will be solving that question. Now, this is very almost impossible to handle. All right. That's the reason why we talk about something called a standard normal table. So the question is, what is a standard normal distribution? Of course, when we say a standard normal table, that's obviously a table that mirrors the properties of a standard normal distribution. So that means from what I just said now, we have a normal distribution and we have a standard normal distribution. And there is something you need to note there. These two distributions, they are similar, but they are different. All right? So what's the difference between a normal distribution and a standard normal distribution? They are both normal distribution, but a normal distribution has a peculiarity. This is a normal distribution. What I just wrote here. X follows a normal distribution mean. All right. For that of a standard normal distribution, we have Z following a normal distribution. All right. But in this case now, the mean is 0, the standard deviation is 1. Now, if you look at what I just said right here, this is a normal distribution, which I've mentioned before. We've talked about this. This right here is a standard normal distribution. That means you can clearly define a standard normal distribution without wasting time, because you can see that what I wrote there indicates something. That means a standard normal distribution is a normal distribution with mean of 0 and standard deviation of 1. Let me repeat that. A standard normal distribution is a normal distribution. It's a normal distribution. You can see I said Z follows a normal distribution. It's a normal distribution, but the normal distribution has a mean of 0 and a standard deviation of 1. All right? That's the peculiarity of a standard normal distribution. The question then you should ask me is, what then is the essence? Why do we need to talk about a standard normal distribution? Now, I just explained a very big problem that can arise from just discussing a normal distribution, is that for each different scenarios Of course, these are just a few. You can go on to write 1,000 or 10,000 or 1,000,000 possibility. Of course, mean can be 5, standard deviation can be 0.1. Mean can be 5, standard deviation can be 0.2. Mean can be 5, standard deviation can be 1.2. Mean can be 5. Just mean being 5, you can have thousands of possibilities. That means for every scenario, you'll be needing a table to handle them, because the normal distribution that has 5 and 1.5 will not obviously work for that of 5 and 1.2. Will not obviously work for 5 and 2.5. So you'll be needing different tables for every possible scenario, which is not feasible. And that's the reason why in statistics, we don't deal with what we call a normal table. No, we deal with what we call a standard normal table. All right. Now, another word being used to identify a standard normal table is Z table. So when you hear the word Z table, you are dealing with a standard normal distribution. Z table. All right. So now, I told you guys already that a standard normal distribution is a normal distribution that has mean of 0 and standard deviation of 1. Good. All right. If you look at something, and you will be able to understand something going on here. The reason why we have a standard normal distribution, of course, which will make us to now have a standard normal table, is that when we have all these many different possibilities, rather than we try to solve all these many different possibilities, all we have to do is something. And this is the word. That's the big word, the very important word when dealing with normal distribution. We standardize. We standardize. So it's a word you'll be using very often while dealing with normal distribution. So we have several possibilities. When mu is 5, when standard deviation is 1.6, when mu is 5, standard deviation is 1.7, when mu is 10, standard deviation is 3.8. Different possibilities. Infinity. None of you here can tell me the number of possibilities that exist there. But rather than we focusing on those different possibilities, all we have to do is whatever you have, just make sure you come back to standardize. So all you have to do is, when you have a question like this, go on and standardize it. Go on and standardize it. The meaning of standardizing is for you to conform that normal distribution to a standard normal distribution. So you have to go on now and conform that your normal distribution to a standard normal distribution, meaning that you will now be able to make use of a standard normal table to solve any problem on my distribution. So you will not be needing to be getting several tables for different scenarios of normal distribution. All you have to do now is to go on and just whatever normal distribution you are dealing with, standardize it. Then you can use just that table I sent to you. That table I sent to you is a standard normal table. That's what we call a Z table. So these are just few possibilities. When we even start solving questions, you will see all the many possibilities. Your mean can be 100. Your mean can be 50. Your mean can be 80. Your standard deviation can be 5.3. Different possibilities. So the thing you just need to do is to standardize that, conform it to a standard normal distribution, and thereby you'll be able to use a Z table to answer it, rather than you needing a special table for it. That's the word you need to get familiar with. Every time you have a normal distribution, you always need to do something. You need to standardize it. All right? You need to standardize it. So the next question, which is a very big question, is okay. All right, you have said all these many things now. We understand what you're saying. Can you now talk about how do you standardize a normal distribution? How do you standardize a normal distribution? Very simple and straightforward. Very, very simple. It's as simple as ABC. It comes with no stress at all. It comes with no stress at all. The only thing you need to understand is the reason why you use it and how to use the table, which is all very simple. All right, so by standardizing, I'm sure you understand what I'm trying to always do now. When I'm trying to standardize anything, that means I'm trying to make that thing come to having a mean of 0 come to conform to what a Z distribution entails. Now, let me teach you something that happened. Let me tell you something that happened. You need to pay attention to what I want to say next so that you don't feel any form of magic was done. You can see right here that I was very, I did not act like I wanted to write X here. I went on to write Z. I wrote it clearly, meaning that something happened here. Normal, we said this was a random variable X before, but now, once we see that this random variable X has a mean of 0 and a standard deviation of 1, we turned that X to Z. We said that's a standard normal distribution. What happened that made X turn to Z? This is what happened, guys. When we had X before, if we subtracted mu from X, what happens there is we have a mean of 0. And if we now go on to divide it by sigma, we'll be having a standard deviation of 1. Many of you, they'll be trying to say, can you prove it? What's going on? You don't need to bother about that. I'm just telling you what happens that turns X to Z is that this X turning to Z at this point, Z, all right, let me just say it this way. Permit me to take this off. This is Z. Just let me say it that way. For you to get Z, that means for you to get Z, which I told you had a mean of 0 and a standard deviation of 1. X, you subtracted mu from X. When you subtracted mu from X, that's the mean from X. You got a mean of 0. When you divide by sigma, you get a standard deviation of 1. All right? That tells you already that for you to standardize, you don't need to start sweating over anything. Whatever was your X value, whatever it was, if you want to turn that random variable, to a Z variable, you just have to subtract the mean, divide by the sigma, and that's all. So the process of standardizing is what I just wrote right here. This is how you standardize. How you standardize is that whatever your X variable is, subtract mean, divide by sigma. You are done. You standardize it. It's so simple. Nothing else, nothing more. All you have to do is, when you have anything, you will see an example now. You know, there's no way I leave this place without giving you examples to solve so that you get familiar with it. Standardizing is the only major skill you have to learn under normal distribution. Apart from you being able to identify your mean and variance and standard deviation, which is always very clearly said in the question, all you need to know how to do, guys, is to standardize and then learn how to use your table. It's more easy than easy can be, I can assure you. And I told you guys at the beginning, you don't need to always shoot yourself in the leg when you are just learning something. Just get patient, follow through. You can't go wrong. But you don't expect that the first time when you're seeing X turn into Z, that at that very moment, of course, if you are very sharp or you have an idea of what is going on, you may. But at this point, it's still premature for you to be blaming yourself for not understanding something. So just try and be patient, and then you will see what goes on very soon. Now, I just gave you something very important, and I'm emphasizing on it so that you understand how simple this is. If you want to standardize, go on, find the mean, get the mean. Of course, I'm sure you guys are smart enough to know that one of the trick that they can give you here is for them to give you a question without giving you the mean, expecting you to find the mean. Of course, that's a story for another day. But whatever you can do, identify the mean, identify the standard deviation. You say I want to standardize it. They gave me, let's say, an instance now. Let me say an instance now when I was dealing with this random variable. This one that has mean of X and standard deviation of 1.5. I said, okay, good. Let's say they told me my random variable has, or let me just say it this way. I'll prove to you guys how simple this thing is. If I tell you something is simple, believe me, it's simple. If you don't believe it's simple, that will be your own decision. But it's quite very simple. I have a question that said my random variable is between let's say 15, or let me just say, let me put 15 here and let me put 35 here. Look at the question right here. Find the probability that x, random variable x, is between 15 and 35. Don't forget, I told you guys that we're using this particular normal division parameter. That means standard mean of 5 and standard deviation of 1.5. Let's say I of course I'm not trying to build up a word problem around this. I just want to give you the how very easy this is. You have a question like this. You have this parameter. You have x variable here. You don't have a table that can handle normal division with this x. You only have a standard normal table with you. How do you standardize this that makes this achievable with a standard normal table, which is what you have with you? Very simple. I want to find probability of x being between 15 and 35. I can't find any table that handles this. I said you want to standardize this, you need to turn it to x. And if you're turning this to x, you turn in mathematics, you don't do something here and don't do it to the other places. So this is what I'm going to do. I'm going to say P. I'm going to start with x. I want to standardize x. Look at what I told you. For me to turn x to z, I have to say x minus mu over sigma. I'm going to decide not to put anything here first. Meaning that, let me clean this up. I wanted to standardize this now. I had x in the middle here. I want to change it to z. I go on to subtract mu, divide by sigma. Meaning that once I do this, I told you immediately that becomes z. Now, but in mathematics, you don't say I do something to the middle, I don't do it to the other side. So you will have to do it to these two sides. But in these cases now, you don't have to be using minus mu or over or just writing it in alphabet or something in this way. You have to go on to fixing the values you have known. So my mean was 5. So I will say 15 minus 5 over what? What's my sigma 1.5? I put that here. For this side, I have 35 minus 5. Of course, mean is 5 over what? Over 1.5. Now, can anybody press the calculator quickly and tell me what this is? This is 10 over 1.5. What's 10 over 1.5? Anybody quickly? Can you give me the answer quickly? Uh, 10 over 1.5 would be 6.667. 6.67, right? 6.67. Probability, okay. And this other side, we have 35 minus 5. That's 30 divided by 1.5. That's 20. Now, look at what I'm saying right here. A very typical example now. This is something you need to know. I had a question. The question said, I should find probability of x being between 15 and 35. Now, you don't have, normally I told you already, this is, if you had a normal division that had this, that you had a normal division that had this whole feature, you just go to normal division and use this. Of course, don't yet start killing yourself on something you have not yet been taught. I've not taught you how to use a normal division, so you probably feel it's difficult. It's not difficult at all. It's so simple. You just check it. It's more like looking at the horizontal and looking at the vertical, and you go and pick your answer. It's very simple. Very, very simple. But you don't have that table that can handle this because you don't have any table that handles it. You only have a table that can handle Z. That's the standard normal distribution. So what you have to do is go on to standardize this. And how do you standardize this? You just go on to do this exact thing. X minus mu over sigma. Everywhere now, for 15, for x, for 35, you have to go and subtract the mean divided by sigma. In this case now, when you subtract the mean and divide by sigma, you're getting z. In this place now, you do the same. Now, look at what we have got now. We're no longer having x between 15 and 35. We are saying z between 6.67 and 20. Now, I told you guys already, just stop right here. Don't yet talk about how to get this. That's a lesson for another day. How to get this is just by looking into your table, which we'll be doing sometimes later. When we get to that place, you will see how easy it is to bring this out on your table. But what I wanted you to learn today is to learn how to make this become this, because you cannot solve using any table from here. You have to standardize. How do you standardize? subtract the mean, divide by sigma, do the same, and that's all. Very simple. It's that simple. There's nothing else to this than what I've said. So let's go on to some questions. I don't want us to just be, let's use some questions to get yourself very familiar with this. Guys, just if you have a pen, please try and jot this down, because I will not be writing this on the board. Of course, I would probably do that when I want to solve this completely. But for now, I just want to teach you how to standardize. But please write this down so you understand how these are the kind of questions that come out. You see it a lot in your exams. Suppose the height of adult American male is approximately normally distributed with a mean of. Suppose the height, or do you want me to write it? Probably I try to. Suppose the height of adult American male is approximately normally distributed with a mean of 176.3 and a standard deviation of 7.1 centimeter. They are both in centimeter, by the way. Centimeter. If you want to write centimeter. All right. So this is the question now. What is the probability a randomly selected adult American male, let me write it as adult American male, AAM, so we don't have to write that over and over again, is taller than 180.0? This is a very good question for us to start with. Suppose the height of adult American male is approximately normally distributed with a mean of 176.3 and a standard deviation of 7.1. What's the probability that a randomly selected adult American male is taller than 180.0 centimeter? This is a very typical question you should be expecting. They'll give you a word problem, and that's why I don't want to do anything less in teaching you. We cannot just be using just figures alone. Let's use word problems to tackle this. So calm your mind and look at what we have right here. Suppose the height of adult American male is approximately, look at what they told you. It's normally distributed. So I told you that normal distribution is a very important distribution in statistics because it mirrors day-to-day living. It has a lot to do with real life experiences. So they said the height of adult American male is approximately normally distributed with a mean. Look at, they told you. That's what I told you. They always tend to, that's what makes this kind of question very simple. They will give you word for word what they are saying. The mean now, they said, is 176.3. All right. And they said the standard deviation, you can see it right here, standard deviation of 7.1. You see how they are so direct with what they are saying. They are not missing words at all. Sigma is what? 7.1. Simple. They went straight to the point. Now, they've told you that means now if we say X represents the random, it's a random variable representing the height, of course. X represents the height of adult American male. So that means X follows, because they told you it's approximately normally distributed. So X follows a normal distribution with mean of 176.3 and sigma of 7.1. Good. That's what I was telling you. It's so direct. They gave you exactly what they are doing. They are not trying to put anything technical or anything. That's all they are. From here to this point, this is the summary. That X follows a normal distribution 176.3 as the mean, 7.1 as standard deviation. Of course, I define my random variable X as representing the height of adult American male. Simple. Now, the next question said, what is the probability a randomly selected adult American male is taller? What is the probability? What is the probability? Probability of a randomly selected adult American male. Of course, since I have said X represents the height of adult, that means I can write X now instead of just writing it word for word. And I explained to you at the beginning of explaining random variables, and that's the main essence of us talking about random variables, is that it helps us to be able to write things rather than writing height of adult. We can just write it in a numerical way. So what's the probability a randomly selected adult American male, of course, probability of X, is taller, that means greater than, taller, greater than 180.0. Simple. That's the question. It's not even, I think, even a newborn secondary school student should be able to solve this. Like, to interpret this, probably not solve this, but interpret this. When they say probability randomly selected is taller, taller means greater than, obviously, greater than 180, taller than. If they say it's less than, that will be less than. Very simple. So what's the probability that a randomly selected adult American is taller than 180.0? Simple. Now, this is where I was explaining, this is where the use of standardization comes in. For all the many things I've said, imagine you had this question and you don't know about standard normal distribution. What you'll be needing to do will be to go and be looking for a normal distribution that has the mean of 176.3 and standard deviation of 7.1, which is not feasible. You don't even have a table like that. That's the reason why we have to do what we call standardization. So what we just have to do now is say, okay, come, we're not going to be using a normal distribution. What we're going to do is to use a standard normal distribution. And the way to conform my normal distribution to a standard normal distribution is by standardizing. So what do I have to do here? Now, rather than trying to find this using a normal distribution, which I don't even have, I will have to go on now to standardize this by just doing this simply. I want to standardize this now. X will have to change to Z. And how do I change X to Z? I change X to Z by saying X minus mu, as I told you already, divided by sigma. That's the way I'm going to change X to Z. I subtract the mean divided by the standard deviation. That's the way I'm going to standardize. And then I have to do the same thing for both sides. So obviously, I'll be having 180.0 now minus, what was our mean? 176.3 divided by, what's my standard deviation? 7.1. Simple. Now, obviously, this will be changing to Z now. Then you can go on to do your calculation for that. If you go on to do that, 180 minus 176, you'll be having 0.521 or so. Now, getting to this point, you're almost done with all your work. I've told you guys, this is so simple. It comes out a lot, but it's a bonus mark for you if you understand this. If you just understand everything I've said, it comes out a lot because they believe that it's a technical aspect of statistics, but it's not. It's a very simple aspect because you just need to go on, interpret your question the way I did. From here to this point was interpretation of question. Very simple to interpret. Then I go on to standardize. How do I standardize? Subtract the mean divided by standard deviation. And that's all. You don't need to do anything more. Just subtract the mean and divide by standard deviation. I do that, I get my answer. Now, this part now is the part where you'll be needing a table, which obviously I've not taught you, and I'm not going to be dealing with this in this class. I'll be doing this later on, probably much later, but I want to emphasize more on being able to standardize. So this is it. if you have a table now, you can use this. You can find this with a table straight up and directly. All right. All right. Now we have to go on to answer the next question, which is for you to find the probability. Now, look at this was the first question. I'm going to give this out to you guys to solve. I want you to find a way to get this. This is the question I'm going to ask you to solve now. All I need you to do now is to standardize this. All right. So the question I want you to try and solve, of course, I don't need you to check a table here, is what is the probability a randomly selected adult American male has a height between 170.0 and 180.0 centimeter, obviously. So this is the question I want you guys to try to answer, and all you need to do is to give me the standard form of this. What's probability a randomly selected adult American male has a height between 170.0 and 180.0? What's probability a randomly selected adult American male has a height between 170.0 and 180.0? So can you give me what the standard form is going to look like? Do we have any answer right now? Do we have any answer right here? What's going to be your form? Now, don't forget, this question is still related to the former question where you have a mean of 176.3 and your standard deviation of 7.1. All right, I have an answer right there. And the person said Z is between minus 0.887. Now, look at how you're going to answer that. Of course, you're told to find the probability a randomly selected adult American male has a height between 170. Of course, you want to first of all interpret that question. Okay, this is question number B. The probability that a randomly selected adult American male has a height between this. That means your random variable X, of course, we're dealing with the height of adult American male. We have 170 and we have 180. Sorry. So this is the question you're trying to answer. The probability a randomly selected adult American male has a height between 170 and 180. All right, this is the question. This is just interpreting the question, nothing more. You have to find probability that x is between 170 and 180, just like they said. Now, you cannot solve this because you don't have a table that can give you this answer. You have to find a way to standardize this. And I told you already how to standardize anything. What you have to do is to go on to subtract the mean and divide by the standard deviation. So simple. Subtract the mean, divide by the standard deviation. So, of course, you have to do to every side. So let me just write this here. That means you'll be having 170 minus the mean was 176.3. The standard deviation was 7.1. The mean was 176.3. Standard deviation was 7.1. So I'm going on now to subtract the mean and divide by the standard deviation. That's all I have to do. All right. And if you go on to do this, you see that you get a probability of minus 0.887. Of course, this will turn to Z, and this will turn to 0.521. All right, that's just very simple. This is how you standardize anything. So, the whole idea around this is to find a way to first standardize. Then at the end of all this now, I'll be explaining in a very much later class how to find this on a table. But the essence of this is to ensure that you guys are very sound with standardization. So let's try this question also to perfect your knowledge on that. Take this down. If a random variable has the normal division with, if a random variable has the normal distribution with mu equals to 82.0 and the sigma is equals to 4.8. All right, so the question is for you to find the probability it will take on a value. So the very first question is the value less than 89.2, B greater than 78.4, C between 83.2 and 88.0, and then the last one, which is D, between 73.6 and 90.4. All right, so I want you to find a way to do this. You have a question that says if a random variable has the normal division with mu of 82.0 and the sigma, which is standard deviation of 4.8, but the final probability it will take on a value less than, the first question is this. So all I need you to do for me in this question is to just bring out, rearrange this and make it conform to a standard form. Of course, we will not be solving the question perfectly because we will not be talking about the use of a table in this class. All I want you to do is knowing how, number one, to interpret the question and knowing how to standardize it. So can you give me the solution to these different questions, the four of them, very quickly? So the very first thing you have to do is to bring out your data. and you have your mean is given as 82.0, and your sigma is given as 4.8. That was clear. Of course, a random variable has the normal distribution. That means we say the random variable x follows a normal distribution with mean of 82.0, sigma of 4.8. All right. So the very first question now is for us to find the probability to take on a value less than 89.2. So the first question is saying find the probability of x being less than 89.2. This is the very first question you have to answer. The second question said you should find it being greater, probability of x being greater than 78.4. All right. And C, x is between 83.2 and 88.0. And D, x is between 90.4 and 73.6. All right. So for you to find the very first one, all you need to do is to standardize this. That will be probability of x minus mu over sigma less than 89.2 minus your mean is 82.0 over our sigma is 4.8. So when you are done finding this, what did you get as your final answer for A? Of course, probability of Z, because your x minus mu divided by sigma will be resulting to Z. So that's the first answer. All right. The second one, the question was for you to find greater. So we'll be having, of course, our x minus mu over sigma greater than 78.4. We're having 78.4 minus 82.0 over 4.8. This will give you probability of Z greater than, when you go on to solve that, all right? What did you get as the next one, the third one? Of course, for the third one, you'll be having x minus mu over sigma, and you're having 83.2, that'll be 83.2 minus 82 over 4.8 less than, then you have 88 on the other side, that'll be 88.0 minus 82 over 4.8. The probability of this. If you go on to solve that, what is the answer you got? If you go on to solve question number C, what did you get as your left-hand side? 83.2 minus 82 is what? Okay, thank you. 0.25 less than Z now, because this will be changing to Z, less than what? 1.25. All right, thank you very much. The probability of this. And for the last one, for D, this is what you have. Of course, this will be probability of 73.6 minus your mean is 82 over your sigma is 4.8. Of course, x minus mu over sigma is what we're doing. Then we have 90.4 minus 82 over 4.8. This is what we call the process of standardization. I'm trying to get you guys very familiar with it before we start solving questions on it. Once you are very good in standardization, all you need to know is how to. So that will be probability of minus 0.75. Yes, is that correct? Sorry, 1.75. Less than, okay. All right. So this is just it. You can see the process of standardizing a normal distribution. Of course, I told you guys already, the main reason why we go about standardizing normal distribution is for us to be able to use a standard normal curve. So let me do a quick recap on everything we have done so far. I started this topic introducing you to the concept of normal distribution, and I told you guys that normal distribution is a symmetric distribution which is symmetric about the mean. All right? I said it is symmetric about the mean. One of the very first things you need to note is that, of course, when you say something is symmetric, it has what we call a bell shaped, like this. If you say something like this now, of course, when I say symmetric about the mean, I told you that means the dividing line that divides this thing into two equal parts is the mean. Now, that mean, of course, as you can identify, will also be the median and also the mode. So one of the properties of a symmetric distribution is that the mean equals to median, which is equals to the mode. All right, note that, very important. Now, I went on to, of course, which something we have done before, which we say, I asked you about the total area under the curve. The total area under this curve is 1. Note that area under the curve is 1. And I wrote the PDF of a normal distribution for you, which I told you guys that you would seldomly use, almost never use in this your JUPEP program. But of course, if you have to do more into normal distribution, you will have to use them. And I explained to you all the components of the PDF. Now, moving on, I went on to identify some of the special features of the curve. Of course, since you know that the whole area is 1, don't forget that the whole area is 1, meaning that from here, the whole area will be 1. But I told you guys one of the special features of normal distribution is that if you have one standard deviation above and below, something like this, this area that is covered here, this is mu plus sigma, this is mu minus sigma. One standard deviation above and below the mean. I told you that area is 0.68. That means it's 68% of the whole area. Of course, if this whole place is 0.68, that means the rest place that we have not shaded will be 1 minus 0.68. If you can understand that, because the whole area is 1, and this place we have shaded is 0.68. And then we went further to talk about what if we have to discuss about two standard deviation above and below. That means probably we'll move a bit further. That'll be mu plus 2 sigma, and then we're talking about mu minus 2 sigma. So we have to talk about this area now, the area that is bounded by two standard deviation above and below the mean. I said the area that is covered by this band is 0.95. That's 95% of the whole area. You need to understand that I may not be drawing the diagram to scale. So just understand the whole concept. Of course, it may not be very perfect since I'm using an hand sketch. Now, for that of 3 standard deviation, mu plus 3 standard deviation, and mu minus 3 standard deviation, of course, the whole area bounded by this space, of course, 3 standard deviation above and below, I told you that is 0.997. That's 99.7% of the whole area. That's just a special feature you need to note in case you are being examined on that. Then I went on to now tell you about how you identify a normal division. It has a mean and a standard deviation. I will say X follows a normal division with mean and standard deviation. All right, that's just a way we write it. Now, I told you that ideally, if you didn't have, let's say you had a function, you drew a diagram and you had a function. What we have always done when dealing with functions is that for us to find the area under the curve, what we always do is to integrate that function. So say we have a function. Let's assume a function 2x squared produce this. Let's assume. If we wanted to find the probability, let's say we have one, let's say this was 5, this was 10, 15, 20, 25, just an instance, 30. Now, if this was a function that produced this curve, and if you're trying to find the probability of the random variable being between, let's say, 15 to 25, if we knew all these things, what you can do is that if you're trying to find this probability, all right, what you have to do is to find the area under the curve if you could. That means the area bounded by 15 to 25, between 15 and 25. That means you want to find this area if you could using geometry. But it's not very possible to do that. And that's the reason why sometimes if you're dealing with continuous random variable, of course, you have to go on to integrate the function. That means imagine 2x squared was what brought about this whole curve. You'll be integrating 2x. So I said imagine, I did not say it was. You will be integrating 2x squared with respect to 15 and 25 being the respective limits. When you integrate this function with respect to this limit, you will be getting the area under the curve. That's the way you find area under the curve. But I told you guys that one other way you can find the area under the curve, apart from using integration, is by checking a table. All right, you check a table. A table is a very beautiful way, simple, easy way of getting area under the curve. Now, how do you use a table to get area under the curve? Now, you have a normal division, let's say for instance, that moves with a mean of 40, standard deviation of 2.5. All right, what you want to do, if you had different normal division table, is to go on to use your normal. And let's say I had a question like this, and I wanted to find probability of maybe x being between the 15 and 25, as I mentioned earlier. What I would have needed to do would have been to pick up a normal division that has this feature. And if I pick up that normal division that has this feature, I will just go and use it to find this straight up. But the thing is, as I told you, there's no normal table that has this feature. If you had to be using, depending on using a normal division table, you would have to create millions of normal division tables because there are different scenarios that can happen. We can have 40 and 2.5. You can have 88 and 2.8. You can have 20 and 4.8. There are too many. It's uncountable. All the possibilities of this. That's the reason why we don't try to even use a normal division table, which don't even exist. What we do is to deal with this and make it conform to what we call a standard normal distribution. And the process of making it conform is what we call standardization, where we try to make it conform to the feature of a standard normal distribution. And what do we do in that case? A standard normal distribution is a normal distribution, of course, that has this feature. The mean is 0, the standard deviation is 1. Of course, we have a table that has this. So instead of us trying to look for many tables, we just find a way to bring this to this form. Now, if I now wanted to find a probability of x being between 15 and 25, Now, I can now do one thing now. I will conform this to a standard normal division, and then use a standard normal table to find it. So how do I conform it to a standard normal division? I go on to subtract the mean and divide by sigma. Once I do this, automatically, I'm changing my x. My x is changing from x to z. And what I just need to do is to go on to subtract, of course, the same, whatever I had before. If this was the thing, I will be saying 15 minus 40 over 2.5. And do the same thing for this, 25 minus 40 over 2.5. This is what I will be solving. Whatever that gave me, this is what I will now be using on my standard normal distribution. It's that simple. It's that simple. That's the summary of everything we have done today. It's that simple. So in our subsequent classes now, we'll be talking about how to get the final solution, to get the final solution after you have been able to standardize, and that will be by using a standard normal distribution. Guys, this is where we're going to stop for today. I believe I've been able to give you a great introduction to normal distribution, and I really wish you guys the best in your understanding. Make sure you take good care of yourself and enjoy the night. All right, guys. Bye-bye.